Thank you very much for coming and joining us online for 136th NIA CFD Seminar. And today's speaker is Mohammed Sayyari. He's a postdoctoral research associate at the Department of Mathematics and Statistics at the Old Dominion University. And he's been around about a year working with Navier Yamaleev. And he got his PhD at KAUST, King Abdullah University of Science and Technology. And his advisor was Matteo Parsani, who used to be at Langley some time ago, and one of our good friends. And he's worked on entropy-stable schemes for various models, and with a wide range of applications, high-speed flows to biomedical flows. And he's been working on currently implicit time-stepping scheme for entropy-stable and positively preserved schemes. So that's what he's going to tell us towards implicit high-order positively preserving entropy-stable schemes for the 3D Navier Stokes equations.
Thank you so much. All right, so as we talked, my name is Mohammed Sayyari, and I'll be presenting on implicit high-order positively preserving entropy-stable schemes for the 3D Navier Stokes equations. So this work is supported by the Department of Defense. And first, I'm going to give some motivation on entropy stability and some challenges that are caused by positivity violations there. And then we'll talk about the regularized Navier Stokes equation, which is the work of Yamaleev and Upperman. And then we'll go to the implicit dual time stepping scheme. So and then we'll discuss numerical results based on that. So I like to start with this slide, and in here, what I have is 3 different schemes. And on the left, we have the Taylor-Green vortex, and on the right, we have the homogeneous isotropic turbulence case, and they're both subsonic. And in check mark is whether the simulation was successful, or cross, it failed, it blew up. And in the top row is an entropy-stable scheme. And in the second and third rows are non-entropy stable. And as you can see, in practice, entropy stable scheme haven't failed any of these cases where you get mixed results for non-entropy stable schemes. Important to say is that this also wouldn't work without the positivity of thermodynamic variables. So yes, entropy stable is good, but we also need the positivity as well. So let's look at the Navier Stokes equations. And the main thing that I want to mention here is that we are not able to get a positivity bound on density because of the hyperbolic continuity equation. We also don't have existence and uniqueness results for non-isentropic flows, and we don't have bounds on the gradients. So let's go first and do the entropy analysis and see how the positivity plays later on. So first of all, the Navier Stokes equations possesses a single entropy flux pair. And to do the entropy analysis, we need these 3 properties. First, we need a mapping between the conserved and entropy variables. This should be positive definite. And then we need to have the compatibility condition for the inviscid flux so that we get a mapping from the inviscid flux to the entropy flux. And then we need a symmetry property that if we change the variables to the entropy variables, then we get a symmetric equation. So to do that, I write the equation in the divergence form, and then we take the entropy variables, which are just the derivative of the entropy with respect to the conserved variables. And then we simply multiply this PD from the left and integrate over the domain. We use the compatibility and just a fundamental theorem of calculus to get the inviscid terms into some boundary data. And then the key operation here is integration by parts. And that gives us some terms on the boundary. And then we get a positive semi-definite term. What's interesting is that now, from there, we can actually get a bound on the time derivative of the entropy with boundary data. And that can be shown to be translated into a bound, an L2 bound on the solution by initial and boundary data. So if you have a bound on the time derivative of the entropy, you get a bound on an L2 bound on the solution.
Maybe better to use your pointer, because online audience don't see this.
Is there a pointer? Here?
Just a cursor.
Oh,
yeah.
Okay.
Thank you.
So here I'm highlighting with this cursor is the bound on the time derivative of the entropy, and that can be translated onto an L2 bound on the solution by initial unboundary. So yeah, try not to point at all. So that's so not differentiate the audiences a little bit. Okay, so what do we do here? So I mentioned that the key operation is integration by parts, and we use summation by parts operators, which give us mapping with this P matrix to the quadrature matrix representing the integration, and the D matrix representing the differentiation. And the SVP operators have the summation by parts property, so we can recast the same operation with integration by parts to a discrete. And this scheme will be built on Legendre-Gauss-Lovato points, or Gauss points with the endpoints included, because we have discontinuous elements, and we'll stitch them with penalties. And these points are computed as the roots of the Legendre polynomials. So to summarize what SVP operators are, we have three operators, and in finite element terms, P could serve as your mass matrix, and Q is your stiffness matrix. And what we have is a property that we can differentiate polynomials exactly up to the order approximation. And we have P is a symmetric positive definite matrix. And that's kind of what we need. So for discretization as well, to get an entropy stable discretization, we also need the compatibility condition discretely. And this work of Fisher, Carpenter, and that we can show that using telescoping operator in this lemma, that we can take this differentiation of the flux discrete. And what we need is we need to employ this complementary grid and a telescoping operator. And the complementary grid comes from basically a one order higher of approximation or of collocation for the LGL points. So if we have here in Q are the LGL points for P3, then the complementary grid points are basically the points for P4. And we have that forming some sort of control volumes, because we actually, the diagonal terms of this P matrix are just the control volume sizes of these, let's say, cells formed by the complementary grid. And everything is stitched together with this telescoping operator, and that gives us, on the right-hand side, a discrete notion of that. So we can recast that again. It just, instead of the boundary of the domain, it gives us on the interfaces of this element. So there's another component that is needed for this to work, which is a 2 points entropy conservative flux. And we need to have that in this complementary grid for the compatibility to work discrete. We also need a symmetric positive semi-definite viscous matrix when we change the variables to the entropy variables. Again, all these properties don't work if we lose the positivity. So one more thing is we need also to, this is the work of Carpenter again, and we have a theorem that shows us that we can take this 2-point entropy flux and have an entropy stable high order scheme based on this formula at the bottom. So that gives us an entropy stable high order scheme for the Navier Stokes, and that in turn gives us an L2 bound on the solution, right? But what happens when you have a high order scheme and the contact or the discontinuity or a jump in the solution, you get Gibbs oscillations. This is the Achilles heel of high order schemes. So if you go blindly, you will hit this obstacle. And this just comes from fitting a polynomial on a joint. So this is just, this will always happen. And the main issue from these is that these are non-local. So you start from here and you can see that it's polluting the whole domain. It causes issues with undershoots, which could go to negative values for density or pressure. And then again, you lose entropy stability, you lose your balance. So let's discuss the positivity preserving by the regularized Navier Stokes equation, which is the work of Yamaleev and Upperman. So this is based on the Brenner Navier Stokes equations. And what's interesting about that is that we can write the viscous flux of the Brenner Navier Stokes equations as just the Navier Stokes viscous flux plus some mass dissipation term. And the main thing that we get from the Brenner is that these provable properties, I'll focus on 4 specifically, which is that we have a notion of positivity of thermodynamic variables because now we have a viscous term in the continuity equation, and we can use that to prove the positivity. And we have existence of weak solutions, and it also is symmetrizable by a family of entropy pairs rather than a single one. And of course, that gives us entropy stability. So what is the regularized Navier Stokes? Well, it utilizes this the additional mass diffusion in the viscous flux only in troubled cells. And so what happens here is that we retain 3 of these key properties, except that we have to revert back to the single entropy pair for the Navier Stokes, because this does not work on every single element. So you'll always have some elements with. You need to use the Navier Stokes entropy stability. But in there, you don't have positivity issue, so you don't need the regularization in all those elements. So with that, we can get high order artificial dissipation, and the main component that we have here is that it's computed based on this residual formulation. And what's interesting about this residual formulation is that what it does, it detects spurious entropy production. So it does not just check if there's if your solution is sharp or not in a certain area. It just checks if you have spurious entropy production, and that's why it's able to distinguish between different waves. So if it's resolved, there's no issue. If it's not resolved, you get spurious entropy production. Then that applies, and it's computed. It computes into this residual sensor, and then that gives us the artificial dissipation in those elements. There's also this new AD max, which is also based on this 2 sensors, a compression sensor and a pressure sensor. And the compression sensors, as it says, it just it's proportional to compressibility, and it just ensures appropriate dissipation and stronger compression zones. And the pressure sensor, it targets mainly these non-physical entropy producing. And these 2 are only going to apply when you have spurious entropy production and not otherwise. Again, what happens with high order? Well, you still don't satisfy the maximum principle. And on the right is kind of the zoomed in picture where you have still some oscillations in there. And so because the maximum principle is not satisfied, then you cannot really maintain the positivity of thermodynamic variables. So what happens is we revert to first order. So for troubled elements, we go to first order scheme. And the key detail is that we don't change the collocation in these elements. We keep everything as is, except we then utilize these control volumes in a similar way to you can think about finite volumes in essence. So now you have everything is going to be done in a first order rather than the high order in these elements. And that is the only way to maintain the positivity for these troubled elements. And now you would say, okay, we have high order schemes, we have high order elements, low order elements. Well, they're stitched together, and we have to have the low order interface talk to a low order interface. So we have the blending cells. This is going to be in this hybrid scheme, and it's just a complex combination of the low order and the high order semi-discrete operators. And this only happens again if we have a violation of the positivity. Otherwise, you only have the high order artificial dissipation. So this is conservative, this is entropy stable, it satisfies the geometric conservation of laws, and it is designed order. So with this, we for explicit schemes, we can get a positivity bound on the time step, but it will still be quite stiff. And for that, we try to turn to implicit to relieve some of this stiffness. And what we would like to have is an implicit fully discrete entropy stable scheme for high Reynolds numbers. And we would like positivity preserving entropy stable nonlinear solvers, which is still not there. So we go to dual time stepping first and try to get the notion of implicitness from there. So what is implicit dual time stepping? Well, what happens is that you simply take your implicit method and you put everything in one side and call that a residual. And then you compute a, basically in here we have a first order in dual time residual. And then we introduce this delta tau, which represents the step in the pseudo time. We will call it the pseudo step. And it works in the way that if you converge in the dual time, then you get back your original step. So you get your original implicit scheme. And these are done, you could do implicit in dual time, but we focus on explicit in dual time because we're trying to utilize the work of Upperman and Yamaleev, which was done on the explicit time schemes. And we'll discuss that next. So there are different ways to choose this residual. So a typical choice is that this residual would be at the same level. So you could either choose the previous pseudo step level, or you can have some combination. And we chose a combination, we're still able to get an explicit update for that. We just need to move things around, but because the semi-implicit operator is in the previous pseudo step, then we can get an explicit update format. So here's the first example with BDF1. For example, we have this update formula. It's just a little bit longer than forward Euler's because we have additional terms in there. And on the right side, we have the forward Euler scheme. And I want to focus on first on the right-hand side. We have the density positivity bound on the time step, which comes from the previous work. And interestingly, when we do the same derivation for this BDF1 dual time stepping scheme, we get a very similar expression, except we have an additional negative term in the denominator. And that's interesting because what happens is that if I reduce this delta t, then this term gets bigger, and then this bound actually gets higher. So even in dual time, not at the time step level, we can increase this delta tau already. So that's one thing that we noticed. Fortunately, the internal energy positivity is pretty much the same because it relies on the intercept, which is C here. Or maybe let me explain this a little bit better. It relies on this quadratic equation, which we form by multiplying the density and the internal energy operator. And so this gives us a quadratic equation. And this is the same as we would do for the explicit in time formulation. And the key thing is that we have that C coefficient is positive, which comes from the previous step. So we ensure the positivity in the previous step. Then we get a positive intercept, and that gives us guarantees a positive root for delta tau here. And that would be the bound on the internal. And this bound is actually quite stiff. And there are limiters that are employed still at that comes from the work of Yamaleev and Upperman. And you have actually velocity and temperature, not pressure. Like so velocity and temperature limiters, which can help with this stiffness a little bit. Still stiff, but it's better than let's say 10 to the minus 12 or 14. That's so that's a little bit better here. So here's another thing that happens. So I talked about this bound on the density, and when we look here, and I want to focus on the left. I guess the cursor is showing, so maybe I explain this better. So what we have in blue is the density bound on delta tau, and at the bottom here, I have a representation of the forward Euler in time value. So that comes from, let me go back. So that comes from the theorem in the right. That gives us the bottom of the left figure. So this dashed line. And so in comparison, we can see that the density bound on delta tau gets much higher as you decrease delta t for the implicit scheme. And there's an interesting point in here is that if you get delta t smaller than delta tau, you kind of don't need implicit anymore. It's too small. There's no need for implicit. So we want to stay within this this half of the figure. And there are two different cases that we have. There are less stiff cases, and then there are much more stiff cases. And what I mean here is whether the density bound is higher than the temperature bound or not. In the left, the temperature bound, I'm assuming it's going to be really high, and that one is less stiff because the temperature bound is generally sharper, but the density bound is less sharp. And this is just from numerical experiments. That's not really we don't have a clear image for this. But when we tested that, we were able to increase the delta tau above the density bound. And we still, even though we violate the density bound, we still don't hit negative densities right away. And so we employ some kind of a function which will detect whether we're getting close to violating density or temperature. And with that, we can actually go a little bit above this bound. And then when we hit a place where we're going to violate it, then that function goes to 0. In the right is kind of the same situation, except that we have the temperature bound much lower. In that case, we cannot play anymore. We cannot try to increase delta tau. Even in the region where we used to be able to kind of maximize it in this kind of triangle, we cannot do that anymore because the temperature bound is much sharper. If you get close to it, if you go above it, you most likely get a negative temperature right away. So we cannot really play with that much. So that will come back in the discussion of numerical results, but I wanted to focus here on what happens with the BDF1 because we have a cleaner expression. We can do the same thing for BDF2. We have an explicit update formula. It looks a little bit more complicated, but it's the same thing. And we have a very similar term that shows up in the density bound as well. But again, it's a little bit more complicated, so we didn't look at analyzing that much. And again, the internal energy positivity is the same picture. You only need to change these A and B coefficients, and everything is the same because C remains always the same. Because those with the dual time stepping, we use a forward Euler in dual time, and so we have the same formula, and that gives us the C intercept, which is going to be the previous density multiplied by the previous internal energy, and they're all supposed to be positive from the previous step. So we tried BDF1, BDF2. Honestly, when I did this generalization, I did it for ease of writing the proof, not really helpful for representing implicit multi-step methods, but I'm just showing you that we can generalize this. And for example, we just pull out the coefficients of these methods in BDF2, and you get these three coefficients, and we can then rewrite the general update formula for the dual time stepping, and that is useful when writing the proof for the positivity bound, specifically for the density. And what's interesting to look at here is that this un+1 is just some coefficient multiplied by a forward Euler-like form. And this R is just the right-hand side of this, basically the semi-implicit operator. And the only thing that we need to do here for the density positivity specifically is as this UMN, which is going to be a combination of the previous pseudo-step solution level and the previous time step solution levels, has to be positive. So if you try to apply this to a different scheme, you just need to make sure that this is positive within the regimes of flow that you're interested in. So with this, we can get a general bound on the on delta tau for positivity of density that will apply on the basically any multi-step method that you're interested in here. And again, the internal energy bound is basically the same picture. So with that, let's get to some numerical results. And we'll begin by discussing steady state case. This is the oblique shock boundary layer interaction. And simply we have this supersonic flow coming in at an angle. Is the cursor showing? Okay, coming in at an angle from here. And it interacts with this boundary layer. And it forms this kind of a bubble in here. So this is the steady state solution. And we start with looking at the Mach 2 case. So this would be the less stiff case in here. And in picture, we're looking at the right-hand side, so du dt, and we're comparing the explicit in time forward Euler versus a few settings for BDF1 using this dual time stepping. And what we have in the running is the total number of explicit steps. So because our dual time stepping is explicit, we want to know how many explicit steps are we spending for each of these implicit steps that we need, and then we just multiply that. And we want to see if the total number of explicit steps is less than just the base forward Euler. So this black line, this dashed black line is forward Euler, and that's kind of the baseline. And as we notice here, we already get a different result. It's much lower in the beginning because of this dissipation. So we'll see the dissipation. Do you want to say something?
I was just wondering the bottom. I just want to make sure I understand the bottom axis is in millions of steps.
It is in millions.
Okay.
That's 10 to the 6. This is the MATLAB notations. Yeah. So yeah, this is 2 million. Thanks for bringing that up. And so what we have in here is that these blue and yellow, which are on top of each other until the end, are kind of very close, but we have a little bit of a better slope at the end with this yellow. And so if you remember from the previous one, I mentioned, well, there's a region where implicit is not necessary. Well, this is what happened with the blue one. So I started with a large time step, and I started to decrease it to try and get a higher bound on the density, so I can increase delta tau, which is what increases, what makes this this slope go down faster. And so with the blue one, I just kept decreasing it, and you reach a line which is basically parallel to forward Euler. In yellow, I kept it just a little bit at 1 order of magnitude higher than the forward Euler step size, and that's the implicit step size. And you can see that you get a better acceleration. And because we could violate a little bit that bound of on the density positivity, we employed this function and we said, okay, if I add to this delta tau some factor multiplied by this function, which ensures that I don't violate the positivity, and I just increase delta tau. And what we see is that it's clearly much better. And I haven't done too much analysis on this, but I could try and add higher and higher to see how much we can get to maximize this. But the initial picture, at least, is that we can get some notion of acceleration for a case like this.
This is a steady case.
This is the steady case, yes.
So you only release the residual by 3 orders of magnitude.
So far, yes. I didn't complete the picture yet. Yeah.
Yeah, well, the discretization error for that problem is also like.
Yeah. So everything is still going down, so we could keep going. But I focus on this region because after kind of around this point, everything starts going down as like linear. Like does not really go there. But
I always forget, but please ask questions during the talk. So.
Yeah, feel free to ask them. So this is the Mach 2 case. When we did this with the Mach 6, we got the other picture, which was that we're not bound by the density positivity, we're bound by the temperature positivity, and that was a sharper bound. So we got nothing. We don't have, and this is not really a complete picture yet, still running these cases, but the initial picture is clear. Your forward Euler is just marching in time, and it does drop. But it seems like this BDF1 dual time stepping scheme is quite struggling. And I've been playing with some of the parameters. You get similar pictures, still forward Euler is winning, but we want to actually run this up to some like much longer time to see whether we actually get acceleration or not.
I can imagine that it will cross again.
Yeah, at some point. I don't know. I wish I know this. I wish I had more computational resources to.
Not conclusive at this point.
Yeah, not
Yeah.
conclusive.
That problem also has a singularity at the leading edge. So that's
That
a
is
true
true,
that's a true geometrical singularity, and that's where
Yeah.
the main problem occurs.
Yeah.
I've got a question. So on these plots, the bottom axis, when you're talking about number of explicit steps, for forward Euler, that's just the number of steps.
That is just the number 7.
For the BDF, you're then taking the cumulative sum of all the dual time steps
Exactly.
across all the outer iterations, correct?
Yes,
Okay.
exactly. Yeah, I'm summing all of them. Yeah. So this way I get a little bit of a fair image. So I
And
cannot-
we use the same number of pseudo iterations at every time step implicit time.
No, actually. So we use a convergence criteria. So we basically take the L2. We take the L2 of this. That would be the absolute.
And you require reduction.
So we reduce it. For this case, we did 10 to the minus 8. So reduce it all the way 10 to the minus 8 in dual time. And in other cases, we use different numbers. But yeah.
I can imagine that this plot is very dependent on this, so that.
It could, but it's a balance. You need to make sure you converge in dual time. So I could try 10 to the minus 7. Maybe I win a little bit more. But what happens at the end is that the dual time error starts to behave. The scheme starts to behave similar to an explicit scheme in a way, at least for this case. Because even though the absolute tolerance is 10 to the minus 8, the error for the steady state problem is already low enough. So everything is low. And you start getting much less steps at the end. So in this regime, even the dual time stepping is not taking too many steps. Most of the steps are happening here, where you have the stiffness.
So you converge to certain level, you're not requiring a reduction by certain number.
We have both. For this case, I'm reducing to a specific level. For time variable cases, I'm using, let's say, 2 orders of magnitude reduction at each implicit step, for example. And then we'll get to that in these cases.
So is there any way of doing implicitness? Are you solving any matrix inverses? Is there a way of
No,
solving
we're basically,
somehow?
we're just doing forward Euler to solve the nonlinear problem. So that's
You cannot satisfy positivity in that case.
yeah, because we want the positivity. So that'll be hopefully next thing on the list, but we didn't get to that yet. So for the wall quantities, they both look the same. So here's the comparisons. There's nothing really to show here. The 2 lines on top of each other between BF1 and Euler, so we don't have any issues with that, with just representing the solution. And I want to look at an unsteady case with the 3D Taylor-Green vortex. And of course, here you need to resolve shock waves, but not over dissipate the turbulence. So that's kind of a challenge typically here. And so for this one, we didn't do forward Euler, we did SSBRK3, and we compared to BDF2. And for BDF2, we ran a few cases, and the BDF2 and SSBRK settings are 64 cubed elements and P6. So they both are 6th order and 64 cubed. And you see here, on the left is the velocity at a line, which is pi and 0 in this domain. And they're pretty much on top of each other. I tried to zoom in a little bit. You see the cursor. This kind of black line and the yellow line and the blue line are quite close. There's a little bit of a difference between the blue one and the black one, and that is more pronounced when we look at the pressure. And you see that's both the implicit schemes of the P6 and the P5 are a little bit lower in this kind of peak in the middle. It's a little bit different from the explicit enzyme SSBRK3. We also look at integral quantities. So we have on the left is the total kinetic energy, and I don't even need to zoom in. They're all for the high resolution ones. They're just on top of each other. But I wanted to use something more sensitive. So on the right is the dilational components of the rate of change of kinetic energy, or time derivative of kinetic energy. So that component is basically the gradient of the velocity squared. So it's much more sensitive. And there you can see a little bit of differences, even at the highest accuracy and the highest resolution. You still see some difference in these lines, but generally they're quite close to each other. However, here's where we finally start to gain something. So what we did here is we took this problem and we ran from a developed state, basically from the state of the solution here. And we ran it for 0.1 time units for both the SSBRK3 and the BDF2 dual time stepping scheme on the same architecture, same machine, same everything. And first of all, we look at the delta T reported, and for the SSBRK3, it's going to be an average because it's computed based on the positivity bounds. But we choose 10 to the minus 3 for the implicit one because we don't have any bound on that one in this case. And for where we get to bound is in this delta tau. So the second, maybe I show the cursor on the second row here. So the first thing you notice is that we're already gaining from that increased bound on the density. So we have this a little bit larger, not too much, but it is sitting higher than the delta T that comes from SSBRK3. And we get close explicit steps, but higher in the SSBRK3. So SSBRK3 is computed based on the stages multiplied by the number of steps. So we're actually counting the stages as single steps here. And then for the BDF2, again, we just take the sum of the explicit steps taken in each of these implicit ones, and then just sum all of those. At the bottom, we have some computed ratios. So I take the number of steps of SSBRK3 divided by the number of steps taken for BDF2. And you can see that SSBRK3 is actually taking longer or like more steps. And when we look at the CPU time, you have like, this is 1.4 the time taken for in comparison to the BDF2 one. So we're actually able to get quite similar accuracy. It's very close, but we're saving like, this is maybe 40%, we can call it, sorts, in comparison to just an explicit scheme, and with maintaining the positivity. So that's kind of the picture that we have for this case. We also ran this hypersonic cylinder case. This is Mach 17.6, and the highest resolution is 55,000 elements, and we use the fifth order. On the left, we have just the Mach number and the bow shock, and then the right, we look at the vorticity. So interesting for us is these wall quantities on the cylinder. And for the reference, the resolution which was much lower than the one we used. So we have this 15,000 P2 case, which matches the reference resolution. So we kind of use that to verify. And for the pressure coefficient on the left side, all the cases are basically on top of each other. I kind of highlight the reference with these dots, but everything is basically same picture. We don't have the same thing for the friction coefficient on the right side, and you can see, like, maybe it's hard to see, but we're kind of following a little bit that these dots, which are the reference, with the 15,000 lowest resolution that we have. We're kind of following that. But as you increase the resolution and you increase the order, you start to get higher peaks in here. And they seem to be converging to something, but it's still not. We don't have a reference for this. So to summarize this talk, we developed implicit dual time stepping positivity preserving schemes for the Navier Stokes equations. And we're doing some of this stiffness that we've seen with this Taylor-Green vortex. We're able to use 10 to the minus 3 in comparison to 10 to the minus 4. And we're able to get some acceleration for the steady state case, at least for the non-stiff one. And we still get the similar accuracy with BDF2 in comparison to SSBRK3. And hopefully this paves the way towards truly implicit positivity preserving schemes for high order entropy-stable Navier Stokes equations. Thank you so much for your attention.
Questions? Andre.
Some questions about the cylinder case. What kind of grid are you using there? Is it curvilinear transformation on a?
It is a curvilinear. I don't have the mesh here, but basically we mesh like some sort of a circle around it, so we get the boundary layer, and then it kind of expands from there. We're not interested in the region in front, but we're trying to resolve a little bit here, but we don't focus on even in the tail as much. So we have open boundaries, supersonic.
So it's basically an O-grid, or is there?
Pretty much an O-grid, but we don't really resolve everything.
Like there is also a wake region where
Yeah.
like, there is a high resolution in the wake region.
Yeah, so in this region is higher.
And it's fully unstructured.
Than
It's
this.
fully
Oh, it's unstructured. And what type of cells again? Hex.
Hex.
Yeah, this is 2D hex and the quadrilateral.
Quads, yeah. We only do quads.
And the Reynolds here is like around 400,000. So it's very high.
Balaji has a question. Go ahead, Balaji.
Yeah, nice talk. Had a couple of questions. Since you're on the cylinder case, I think it would actually be useful if you pick the Mach 16 cylinder case by Holden. I think there's enough data to plot CP, heat transfer, which is much more of interest to the community. I know in the numerics, a lot of people use this Mach 17 case, but it has no data and there's no reference. The reference data is from computation. So there's a data from Kubrick called the Mach 16 cylinder. So that's just a comment.
Okay.
But we don't simulate the turbulence. So this is a lamp.
No,
Okay.
it's not. Turbulence is of not importance there as well. So there's a lot of people are just doing laminar Navier Stokes. Yeah.
Yeah, we'll take a look at that. Yeah. I haven't considered it.
Can you go to the flat plate boundary layer? I mean, oblique shock boundary layer interaction.
Yeah.
I
So
don't
this
think
one.
you mentioned how many grid points did you have for this case, and like what is the resolution and what is the Reynolds number for the boundary layer?
So for this one, we used, this one is a 27, so this is the Mach 6 case. This is 27,000 elements. I actually forgot the Reynolds number.
I think it's 10,000.
Yeah. Yeah, it is 10,000. Yeah.
So I was just curious on like what is the wall normal resolution, because if I remember right, in the next plot, the number of iterations you show is like of the order of 2 million or 3 million.
Yeah. Yeah.
For a steady state case, supersonic, don't you think it's quite excessive?
So, okay. So you see, if you see, so from, if you see the x-axis, from minus 0.2 to 0 is just an Euler wall. And then at 0 up to the end, you actually have a viscous wall. So at 0, you have this kind of a singularity. And that's generally the issue. This is what generally keeps the right-hand side from going down. So that's...
Yeah, so one solution is like usually when we do these flat plate at supersonic conditions, we try to round off the leading edge. So you could have like an elliptic leading edge with a very tiny radius that would help you avoid the singularity. Yeah. And that might maybe relax the stiffness
yeah, but this
in
is
that
like
region.
simplifying the problem rather. So we're trying to get the problem as is rather than try to simplify the geometry.
And we also had a reference solution for the Mach 2 case. So that was another reason why we picked that particular.
Yeah, but the leading edge won't affect it so much. It'll just help your simulation, the grids and everything, so smoothness and stuff.
Yeah, you can stick the blazers, you can do a lot of things, but just we try to use exactly the same setting that was in that. It was some high order conference, and I forgot the name.
Yeah.
Okay, thanks. That's all my questions.
Oh, thanks. Yeah.
Any other questions?
I have a question, but maybe not about your work.
No worries.
About the previous, naive, basically.
Fair.
So this sensor that you use in order to introduce additional viscosity, I think, in the residual, so that the sensor is basically like step function, right? So that if your S is, say, greater than some delta, and you introduce this term, otherwise
it's not. I mean, this is oversimplified. It's not exactly like that. So there is a cutoff. So you're saying about smoothness of the sensor.
Exactly.
Yeah. It's of course. We also saw that. It's we didn't really spend time trying to clearly smooth everything out. So it's kind of there is a non-smoothness in the dissipation operator, and that hurts actually. So you need to carefully smooth it out. I mean, it's not a big deal, but it's from the point like writing the formula, but cleaning up the code, it will take.
Just recognize the importance.
Yeah.
It should not be smooth. It should not be like step function.
Yeah, but it's not a step function.
Okay.
Yeah.
Okay. Thanks.
So have you, in an implicit setting, let's imagine that you're using Newton's method. And Nell was saying that you can't really enforce positivity in that regard, but imagine that you're using Newton's method and you solve AX equals B at a particular Newton interval. And then you enforce all of your machinery on the update. So you've gotten your AX equals B gives you a delta U.
Yeah.
And that delta U will obviously violate your positivity constraints. Is there a way of putting your machinery on the delta U as opposed to putting it here on your time step?
So I haven't thought about that in this way.
There are too many constraints.
Yes.
Yeah, you need to satisfy the conservation when you start tweaking your delta T, delta U. You need to satisfy the entropy stability. You need to satisfy the positivity, and you need to do that all together. Of course, not to mention GCL and all other stuff.
Yeah.
So it's kind of theoretically yes, but practically it's it needs to be proved, not just simply.
And there was, I think, work. I forgot the names of the authors, but there was already work on positive preserving like nonlinear solvers. But
there's work by there's a guy over at Lund, Philip Birkin.
Yeah,
doing there are all kinds of interesting things that happen with Newton's method.
Yeah.
It believe it or not, it preserves certain invariants. I don't recall exactly which one.
Wasn't part of the show one of his papers that if you're using generalize, you do preserve conservation regardless of your distance?
Yeah, I remember seeing that paper. I found it hard to believe, but
Yeah,
that was in the paper. I haven't dug into it. But I mean, if that were the case, if you did if some things come along for the ride, then perhaps it isn't.
That would be nice. Yeah. I think I remember they said like if they could take any semi-implicit kind of operator and then just work on that, but I forgot exactly what
The whole idea is to project back on the entropy manifold. That's what they're trying to do. That's a whole trick in run to cut.
Yeah.
Where you establish the nonlinear manifold. In principle, you know what that nonlinear manifold is. You violate it, and then you project back onto it. At the end of the time.
And that's what we did with the relaxation for explicit schemes.
Yeah, but this is the entropy conservative manifold, not entropy dissipative manifold. That's because we need the entropy dissipative. And of course, it's not. I mean, that there's just a bunch of these manifolds. It's just going to depend on how much you are dissipation adding.
You still compute like so for the relaxation goods, for example, you could do it for viscous problems.
Yeah, you can do the inequality, but the question is like it's inequality. So by how much you are kind of going away from that inequality?
You still compute gamma roots, like puts you on some manifold. I don't know exactly whether what that looks like, but it puts you back on.
But for relaxation RK, the problem is that proof for the roots, it's only available for a smooth case. So as long as you have a discontinuity, just pretty much everything falls apart. But nobody tells about that.
Balaji, do you still have a question?
Yes, since you're on the slide, I was just
thinking
about how would you extend this if you had species equations, chemistry, because you're talking about high-speed flows. So this Fourier's entropy protection residual formulation, how would it act when you have chemical reactions and like your general framework, how would it change?
I'm not sure for chemical reactions what that would look like. I mean, we'd have to look at the species.
Yeah, you have just a bunch of continuity equations for each species. You'll have a bunch of ODEs for chemical reactions. So for each equation of the continuity equation, you'll get the similar constraints, of course, depending what kind of stiffness from each species. I mean, each species has. So then you'll have to go and generate the global mean out of that.
Yeah.
So, and then of course you'll have the contributions to the other terms as well. But overall, it's it's going to be very similar. Of course, the stiffness is going to be way more higher. And then of course, especially the temperature constraint is going to be horribly bad because of the Reynolds law. But if you kind of in terms of the framework, it will stay pretty much the same. But the stiffness may get you.
But so you would have an additional constraint on the total, and I mean, like in terms of density, because now you have multiple species. What would
Yeah,
be
yeah, but
the
it will
positivity
be.
constraint on the density for that?
Yeah, you can do analysis for each. So you have a bunch of continuity equations. So you have the now similar analysis for each species, and then each equation or each equation for each species will produce its own constraint on delta t, and now you have to take a minimum out of that. So and then just.
And that's what we're already doing with the temperature and density. So it's just an extension of that same idea.
But there will be some diffusion of species equation.
Yeah, but we also have artificials.
Yeah, you need it for the proof of the density positive dynamics.
Thanks.
Yeah, and you have to bound each species has to be bounded 0 to 1.
Yeah.
Yeah.
You can always normalize.
Yeah.
We have 1 minute to noon, and I guess it's about time we have to go to lunch, so we continue to discuss at the lunch. So thank you very much, everyone, and thank the speaker once again. Thank you. Thank you, everyone.